In the spring of 1972, in a basement laboratory at Berkeley, a young physicist named John Clauser spent his nights heating calcium atoms until they glowed, aiming the light at two detectors on opposite walls and hoping the numbers would come back wrong. He had been warned about this. Older colleagues told him, kindly enough, that no career survives this particular question, that it had been settled 40 years earlier by people far cleverer than him, and that whatever he measured would end up as a footnote to somebody else's certainty. He built the machine anyway, because he believed Einstein had been right, and because he wanted to be the one holding the proof. To understand what he was hoping for, you have to go back to a paper Einstein published in 1935, which was less a discovery than an accusation. The setup is simple enough to describe at a kitchen table. Some events throw off two particles at once, and those two particles are bound together by the physics of their shared birth, so that whatever you eventually learn about one tells you something about the other. Send them a kilometer apart. Measure the first. The second is now settled too, instantly, whatever the distance. On its own, that isn't remarkable. If I tear a ticket in half and mail the halves to different cities, opening one envelope tells you what's in the other, and nobody phones a physicist about it. But quantum mechanics was making a much stranger claim, and Einstein knew it. The theory doesn't say the particle has a property we haven't learned yet. It says there is no property yet. Not a card lying face down, waiting. A card with no face at all until someone turns it over. Which left, Einstein argued, two possibilities, both fatal. Either the particles were carrying their answers the whole time, sealed inside them like the ticket halves, and quantum mechanics was an unfinished sketch that hadn't found them yet. Or measuring here genuinely reached across the distance and settled something there, in a way no signal could travel fast enough to explain. And he wanted no part of a universe that behaved like that. He spent the last 20 years of his life betting on the first option and losing patience with everyone who wouldn't. Everyone agreed the question was untestable. It was a matter of temperament, a thing you argued about at conferences and then went back to real work. Then, in 1964, a man named John Bell noticed something everybody else had walked past for 3 decades. Bell had grown up in Belfast with no money for university, left school at 16 for a job cleaning glassware and setting up demonstrations in a physics department, and eventually talked his way into being a student in the building where he'd been the technician. By the 60s, he was designing particle accelerators at CERN, and he worked on this problem in the evenings, on his own time, mostly because it bothered him and wouldn't stop. His insight was to stop asking both particles the same question. Vary it. Turn the detectors to different angles. Run the experiment thousands of times with different combinations, and then look at how often the two sides agree across all of it. Because here's the thing about answers written in advance. A fixed list can only be so consistent with itself. Sealed instructions have a ceiling on how much agreement they can produce across a range of different questions, and Bell worked out exactly where that ceiling sits. Quantum mechanics predicted agreement above it, which meant the argument was no longer about taste. It was about a number, and somebody could go and measure the number. Almost nobody did. The paper sat in an obscure journal for years. Then Clauser found it and built his machine and ran it, and the correlations came back above the ceiling, sitting exactly where quantum mechanics said they would sit, and nowhere the sealed instructions could reach. He checked it again. He has said since that he was disappointed for a long time afterward. He had wanted the other answer. Everyone since has gotten the same result. Alain Aspect, in the early 80s, rebuilt the experiment so the detector angles flipped while the light was already in flight, too late for any warning to reach the other side. Others separated the detectors by kilometers, then by continents, then used a satellite. Every objection anyone raised got engineered away, one by one, until the last of them closed in 2015. And in 2022, 50 years after those nights in the basement, John Clauser flew to Stockholm to collect a Nobel Prize for the experiment he had hoped would fail. So what does it leave us with? Not a way to send messages. Look at one detector on its own and you see nothing but noise. And the noise looks identical no matter what anybody does at the far station. The pattern only exists in the comparison of the two records, and to compare them, you have to carry one to the other at ordinary speed. Like everything else in the universe, nothing arrives early, nothing arrives at all. What breaks is quieter than that, and harder to live with. It's the assumption that two things separated in space are two things, each with its own private set of properties, each complete in itself, that the world is made of parts, and the parts have their own facts. The pair has a state. The halves don't own pieces of it. Pulling them apart doesn't divide anything, because distance was never what was holding it together. Einstein saw all of this in 1935. He laid it out precisely. He understood exactly how strange it would be, and he was right about every part of it, except the conclusion. He had assumed that a picture of the world this unbearable could not be the true picture. That assumption was the only thing in the paper that was wrong.